Hello everyone. In this video, we will learn how to determine the maximum moment in the beam, including the following key points in determining the support reaction, drawing the shear force and bending moment diagram, and explaining a simplified approach to find the maximum moment using the shear diagram and the method of section. So let's dive into our problem. Determine the maximum moment of a beam carrying a uniform load and a concentrated load as shown in a figure below. So here we have a load diagram for this beam. We have the 50 kilonewtons per meter uniformly load extended from point A to point D. And also we have 20 kilonewtons per meter from point B to E, which is in the cantilever end. And we have a 5 kilonewton applied at the free end of the cantilever end. And from point A to B, we have a concentrated load of 45 kilonewtons applied at point C and 60 kilonewtons applied at point D. So let's get started with our solution. Determine the reaction at support. So first of all, we need to determine the reaction at point A and B before we can draw the shear diagram. Now we will choose any arbitrary location, whether you can sum up moment at point A or B. So that is positive clockwise based on our convention. Summation moment at A, let's say at this point, is equal to 0. So minus RB times 5, which is the moment arm from here to there, to the reaction at point B is equal to 5. Plus 45 times 1.5, that is the clockwise due to this load, plus 16 times 3.5 due to this load, 3.5 from here to there, plus 50 kilonewtons per meter times 3.5 squared over 2. That is the 50 kilonewtons per meter from here to there. Plus 20 times 1.5, that is the uniform load at the cantilever end, times the moment arm, measured from the center of the uniform load to the point A, which is equal to 1.5 divided by 2, this one here, plus 5, plus 5 kilonewton times 6.5. That's the lever arm from point A to E. Total length is 6.5 and that is equal to 0. So to calculate RB, it's equal to 126.95 kilonewton. And that is the reaction at point B. So for the reaction at point A, by summing forces along Y positive is equal to 0. And that is 126.95, this is upward load, plus RA minus 45 kilonewton and minus 16 kilonewtons due to this concentrated load, minus 50 kilonewtons times 3 kilonewtons per meter times 3.5 meters, which is this one, minus 20 times 1.5 at the cantilever end, minus 5 kilonewtons, which is this one. So to calculate the reaction at A is equal to 144.05 kilonewton. Now, we have determined all the reaction at support. So we can now proceed to draw the shear diagram. So the shear diagram, we have here all these diagram for the shear based on the loading scheme that we have. So let's break it up step by step. So at point A, shear at A is equal to the reaction at A, which is equal to 144.05 kilonewton. Now between A and C, we have a uniform load downward. So we have the linear, in the shear diagram, we have a linear first degree and negative slope. That is negative slope for uniform load. So at this point C, at C, the shear is equal to 144.05 minus the load between A and C. So to calculate that, C is equal to 144.05 minus 50 times 1.5 is equal to 69.05. This one here. This is the shear just to the left of at point C. Now, at this point, we have a concentrated load of 45 kilonewton. So 69.05 minus 45, that would give us 24.05. So it drop it down because we have a dropping load of 47 kilonewton. So from this point, 24.05, this is the shear just to the right of point C. Now, between point C and D, we have a uniform load. Again, we have the linear first degree. So at this point, if you notice this one, we have a zero shear at this point. The transition between the positive shear to the negative shear. Which means at this point, this is the zero shear. And remember, at zero shear, that is the location as well as the location of our maximum moment at this point. So that is equal to 0.48. I did not show the calculation of how I come up this figure because this is only for the ratio and proportion. So this is just a simple calculation, ratio and proportion. Similar triangle. Now to calculate the shear at point D, and that is equal to 24.05 minus 50 times 2, which is the uniform load between C and D. So 24.05 minus the load between C and D, and that would give us 75.95. This one here, this calculation here. Negative 75.95. That is the shear just to the left of point D. Now we have a dropping load of 60 kilonewtons, so negative 75.95, it will go farther down to negative 91.95 because of 16 kilonewton. So this is the shear just to the right of point D. Now between point D to B, we don't have any load. So our shear diagram is constant. So at this point, at point B, we have the upward load due to the reaction at point B. So what is that reaction? Minus 91.95 plus the reaction of 126.95. So the calculation at point B is equal to negative 91.5 plus 126.95 is equal to 35 kilonewton. That is positive. So going up, that is positive. Now, this is the shear just to the right of point B. So what is the shear at point E? We know that shear at point we don't have anything here, that it should be 0. So the shear at point B is equal to 35 minus the load between B and E. So 35 calculated here, shear at E. 35 minus 20 times 1.5, that is equal to 5. Here we have 5. We have not yet dropped to 0 because we still have concentrated load of 5. So this is 5 kilonewtons, that is negative, downward. Then it will go down back to 0. So we have 0 at this point because we don't have any shear at this point. If it so happens it is not equal to 0, so you will need to check your previous calculation here. Maybe there's something wrong. Wrong here. So it is normal sometimes there is a discrepancy of 0.01 or 0.02. That is due to the rounding off of numbers. So now we are done with the shear diagram. We can proceed now to draw the moment diagram. So how to draw the shear moment diagram? First of all, I have already drawn this moment diagram. So let's break it up step by step. So we have the A, let's say the maximum moment can be determined by calculating the area under the shear diagram, starting from the point of zero shear. So the maximum moment, we have determined the maximum moment at zero shear. So that is equal to the area under the shear diagram. So that is equal to the area of a trapezoidal plus the triangular, the small area here. So let's break it down. Moment at point A is equal to 0. Whether it is a pin or roller should be 0. So between A and C, we have a linear that is first degree. So if it is first degree, it follows the moment should be in second degree, which is parabolic. If you express it in equation, it involves with x squared, which is quadratic equation. This one is linear. So this one is second degree. First degree, second degree. So the moment at point C is equal to the area under the shear diagram, which is equal to moment C here, 0.5 times 1.5 times the average of 144.05 plus 69.05, because this is a trapezoidal load. That is equal to 159.8. 159.8 here. So the maximum moment at this point here, we have the zero shear, which is equal to 0.48 from this point to that point. We have a similar triangle because this one is linear. I did not show the calculation how I come up this 0.48, but it's only a simple calculation because just ratio and proportion, similar triangle. So here at this point, at point D, the moment at point D is equal to 165.6 times the area under the shear diagram. So which area? From this point up to that point, that is the triangular load, triangle. So the moment at this point is equal to 165.6 minus 0.5 times 1.52. From this point to that point, 1.52 meters times 75.95, which is this one, not this one here. And that is equal to 107.9. So that is only the pattern, guys. When you calculate again at point B, so in the same manner, you have to add the moment from this point, then minus the area under the shear diagram, minus if it is negative, plus if it is somewhere here, if it is positive. So the moment at point B is equal to the moment at point D plus the area between D and B, which is 107.9 minus 91.5 times 1.5. So this part here is the area, 91.95 times 1.5. So that is the area at this point, which is equal to negative 30. So if it is negative 30, this is the moment just to the left of point B. Now, without calculating this at cantilever end, if we calculate the moment at the face of the cantilever end, it should be negative 30. Otherwise, there is something wrong with your calculation. So to calculate that moment at point at the cantilever end, so here at the cantilever, this is also one way how to check whether our moment diagram is correct or not. So to calculate the moment at the cantilever end, which is minus negative 20 times 1.5 squared over 2 minus 5 times the moment arm to 1.5. So to this one here, that is equal to negative 30. So it should be negative 30. If it so happen it is not equal, let's say 30.02, that's okay because that is the discrepancy is due to the rounding off of the figure here. Now at the moment at point E, we don't have any moment there because that's free end. It should be 0. So there is an alternative solution to determine the maximum moment. The tricks here, if you are just asked to determine the maximum moment, when you drew the shear diagram, once you determine already the location of zero shear, you don't need to draw the moment diagram to save your time if you are especially if you're taking the exam. If you encounter this kind of problem, I don't think so. If you have this problem, this is a little bit complicated. So at this point, you can sum up moment at this point by method of sections from here to there. That is 1.98. The location where the shear is 0. So this is only the way where we can determine the maximum moment using the method of sections. So at this point, if you sum up moment at this point, that is 144.05 times from here to there, that is 1.98 minus 50 times 1.98 squared over 2 minus 45 times 48, that is due to the concentrated load. So the total of maximum at this point, where the shear is 0, that will give us 165.6. So that is the same figure what we have here in the using the shear diagram, 165.6. By the way, guys, in the method of section, this is another alternative to give you a choice, because in the shear diagram, if just in case the load is first degree, let's say trapezoidal, and your shear diagram is parabolic. Now you cannot calculate this as trapezoidal if it is parabolic. So either you use the formula of the curve, there is a formula there in the book, or you can integrate to determine the area by integration. That's fine if you are comfortable. So either you use this method of sections. For me, I prefer to use this rather than to integrate. Or some other people, other students, they are comfortable to integrate. So you have the choice which method you're gonna use to determine the maximum moment. And by the way, guys, for those who are not familiar to the moment diagram, and I will just let me to explain how I come up this diagram for the moment. So from A to C, this is the second degree because our shear diagram is first degree. So this is a second degree, which is parabolic. If you express this in an equation that involves of x squared, which is quadratic equation. So parabolic at this point to this point here, which means if it is a positive shear, and this one in the moment diagram is positive slope, meaning the slope here is going up. But at the point where the shear is 0, the slope here is horizontal, which means the slope is 0. This is what we call contraflexure, the transition between the positive slope to the negative slope. But here at this point, to that point there, the slope is negative because negative shear. So it started to go down from here. So it is linear. This is also second degree. That is still parabolic at this point. But from this point to that point here between D and B, our shear is constant. Shear diagram is constant. So if it is constant, from this point to that point is linear. It is not curved, it is linear. So we have the negative slope because we have the negative shear. But at this point here, from point B to E, we have the positive shear. So our moment diagram is positive slope. It will start to go up, then it will start to go to zero moment at this point. So that's all for today's video, guys. And if you find this video helpful or you enjoy this video, please don't forget to like or subscribe so that you'll be updated for the next upload. Thank you for watching. See you next time. Bye bye and God bless.